In this lesson, we will talk about pointers as return types for functions. A pointer is just another data type. It's just that a pointer stores the address of another data type. So it is quite possible for a function to return pointer, but we must understand the use cases in which we may want to return a pointer from a function. So let us try to understand this. I'll get started by writing some code. Now I want to write a very simple C program initially. I want to write a function add that will take two integers as argument and sum these two numbers and return the sum. So let's say we declare another variable C, and C is equal to a plus b, and the function returns C. Now in the main method, I'll initialize two variables. Let's name these variables x and y. Let's say x is equal to 2 and y is equal to 4, and we will have another variable z, which will be the return of this function add, and we will pass x and y as arguments to this function. And finally I'll print something like sum is equal to z. No prizes for guessing the output here. I'll modify this code slightly, but before that I want to talk about this concept once again, that x, y and z are local variables to main function, and a, b and c are local to add function. And what really happens when we call the add function is that value in this variable x of main is copied to variable a of add, and value in y of main is copied to b of add. And what if we name these variables in main a, b and c instead of x, y and z? If we run this code, output will be the same. This time what we will say is that the value in a of main is copied to a of add, and the value in b of main is copied to b of add. This a in main and this a in add, they are not the same. You can verify this by printing something like this. I'm printing the addresses of these two a's in my code, and as you can see, address of a in main is something like 2883032, and in add it is 2882792. So they are not the same. That means these variables are not the same. They are at different memory addresses. The names of variables are local or specific to a particular function. In our example here, the function main can be called calling function, and the function add can be called called function. In this particular call, when we are saying that C is equal to add and passing a and b, and this call where a and b in main are getting copied to a and b in add, this is called a call by value. This can be called a call by value. Now what I want to do is, instead of passing by value, I want to pass the addresses of these two variables. So I want to say that I want to pass address of a and address of b to the add function. So the signature of add function should be such that it should receive the addresses. So I'll say that okay, it takes two pointer to integers a and b, and now we can access the values at these addresses by using this asterisk operator, which is used to dereference an address. Now such a call is called call by reference. A and b are integers local to main function, and in the function add, a and b are not integer variables. A and b are pointer variables, pointer to integers. So their type is different. They are not int, they are int star. But at the end of the day, they are also variables which are local to the function add. It's just that they are not integers. And now I'm using these two variables, which are pointer to integers, to access these two variables a and b in the main method. And to do so, we use the asterisk operator, and now this code should also work. I'll write a few more print statements inside this function add. I have tried to print a, and I have tried to print asterisk a, and initially I was printing ampersand a. So now ampersand a should give us the address of the pointer variable. A should give us the address of a in main, because that is what this variable stores, and asterisk a should give us the value of a in main. Let us see the output. As you can see here, the address of a in main is 3537612, and address of A in add is something else, but the value in A of add, which is the address of A of main, is equal to 353762. So the first and the third line are same, and using the address we are printing the value, which is equal to 2. I had a spell mistake here. Now I'll clean up some of these print statements. Coming back to our function add, we are returning this value C, and once again in the main method we are collecting this value C in another variable, which is C of main. Why not do something like pass the address of this C in add function? So what we will do now is we will say that we want to return a pointer to integer from this function, and here we will return ampersand C. Now ampersand operator, when it is put in front of a variable, it gives us the address. Now of course here we will have to collect this particular address, so we will have to define a pointer variable. Now this would be okay, and when we are printing, we will have to print the value at address being pointed to by this pointer variable. So what we just did is we modified this add function to return a pointer to integer. There are two syntax. We can say int and then put this asterisk sign, or we can say int and then put this asterisk sign in front of the function name add, and both these syntax are valid. Now this function is returning pointer to integer. Let us run this program and see what happens. Let me also strike off this print statement here. Okay, so the output seems to be alright. Now have you caught some logical error with this code already? If you haven't, stay with me for some time. Now what I want to do is I want to write another function, a simple function that will print hello world. So I'll name this function print hello world, and in this function I'll write a simple print statement. And now before I print this sum, what I'll do is I'll call this function print hello world, and let's see what happens now. Oops, this looks weird. Sum is not correct now. I just saw that it was coming fine in my last run when I did not call this print hello world. What happened? So let's try to understand what really happened here. I'll come back to this familiar diagram of various sections of applications memory. The memory that is allocated to a program is typically divided into these sections. All the local variables and the information about function call executions goes into the stack. So let us run through this code. Let us simulate this code and see what's really happening in the memory. For each function call, some part of the memory from the stack is allocated for its execution. We call this the stack frame of that method or that function. When the program starts executing, first the main method is invoked. So in the stack frame, some memory will be allocated for main function, and all the local variables of main function will live inside this stack frame. Let's say the starting address of this stack frame is 100 and the end address of this stack frame is 130, and we will have three local variables created here: a, b, and ptr. A and b are integers and ptr is an integer pointer. Let's say a is at address 100, b is at address 112, and ptr is at address 120. I'm just making these assumptions. Now when the main method will come at this line where it is calling add function, its execution will pause, and now memory will be allocated for the execution of add. At any time, whatever function is at the top of stack is executing. Main method will wait for add function to complete and return. So here I should say a is equal to 2, b is equal to 4, and now add comes here in the stack. Let's say add gets memory from 130 to 160, and add also has three local variables, a, b, and c. A and b are pointers to integers. The value of a will be 100 and the value of b will be 112. Let's say their addresses are 130, 140, and 144. Once again, these are just random assumptions. Now c is calculated as asterisk a plus asterisk b. A is pointing to this location and b is pointing to this location. Asterisk a is value at address stored in a, and asterisk b is value at address stored in b. So this c will be 6 here. These two values will be added. Now this add function will return the address of its local variable c, which is 144, and finish its execution. So this PTR will be 144, and now the memory that is allocated to add function will be deallocated. Now this memory above address 130 can be used for other function calls, and even though this variable pointer PTR stores the address 144, stores the address of this particular block, it kind of points to this particular block. The data here is not guaranteed because this memory has been deallocated. Now we come here to this print hello world, and now a memory from stack will be allocated for print hello world above this stack frame of main method. This is main. So let's say that print hello world gets this memory block from address 130 to address 150. There is no local variable in this print hello world function, but still function call execution involves storage of some information. So now this section from 130 to 150 is for print hello world. I'll write phw as shortcut for print hello world, and it has been overwritten. So this block at 144 no more stores value 6. So when we come here at this print statement to print the value at this particular address, we get some garbage value. Now the obvious question would be, why did we get the right value when we were not making a call to print hello world? I would say that I just got lucky. Maybe because I did not call any other function after making a call to add, my machine did not overwrite or erase the data at that particular memory location. But when I made a call to print hello world, that memory got used. If you see, we have passed the addresses of these two variables a and b of main to add function, but that is alright because called function always comes above the calling function in the stack. So anytime this called function is executing, calling function will be in the memory. So if add is executing, main is guaranteed to be in the memory. So addresses of variables in main will be accessible to add. But if we try to return a local variable from the called function back to the calling function, like if we want to return a local variable from add to main, then when that function finishes and the control returns back to the calling function, that memory has already been deallocated. So it is okay to pass something from bottom to top in this call stack, or I should rather say that it's okay to pass a local variable, the address of a local variable, from bottom to top in this stack, but it is not okay to return the address of a local variable from top to bottom in the stack, in the call stack. I hope this makes sense. So now the obvious question would be, what are the use cases in which we may want to return pointers from functions? Well, if we have address of some memory block in the heap section or some memory block in the global section, then we can safely return the address of these blocks, because anything in the heap has to be explicitly deallocated. We control its deallocation, unlike stack. And anything which is in the global section, a global variable, lives for the entire lifetime of the program. I can use malloc or new operator in C++ to get some memory on heap. So if I modify my code something like this, I will declare this C as a pointer to integer and get some space allocated on the heap using a call to malloc. Now malloc is a library function that returns pointer, but it returns pointer to an address which is on the heap. So we get a memory block, and using this pointer variable now, we can write this value asterisk a plus asterisk b at that particular memory block, and then we can return this address c, which is the same address that malloc returned us. But we are safe now because we are returning address of a block which is on the heap and not on the stack, and this will work now. Now in this code, let's say this call to malloc gives us this block at address 500 in the heap. C now is only pointing to this block, and using C we have written this data here, this value 6, and now when add finishes, the address returned by the add function, which is address 500, is still valid. We still have the data there, and it will not be deallocated. Anything on the heap has to be explicitly deallocated. So while returning pointers from functions, we need to be careful about the scope. We must be sure that the address is not reused to store something else, or the data is not cleared from that address. In most cases, we will be returning pointers to memory that is allocated on the heap, or memory that is in the global section, the global variable section. In our coming lessons, one place where we will be using pointers as function returns in our code is implementation of linked list data structure. So this was pointers as function returns. Thanks for watching.